Consider the following problem based on example 13.4. If 2 moles of ethylene is mixed with 1 mole of water and it's allowed to reach equilibrium at 145 degrees Celsius in a reactor that is controlled at 2 different pressures. In the first case, the pressure at equilibrium is 1 atmosphere. And in the second case, the pressure at equilibrium is 2 atmospheres. And we are asked to calculate the composition of the equilibrium mixture for each of the 2 pressures at 145 degrees Celsius. In the previous lecture, we already determined our equilibrium constant, and it will not change because it is not a function of pressure, only a function of temperature. We previously showed that at equilibrium, this composition-based term must be equal to our equilibrium constant at that temperature. We are going to assume ideal gas behavior, and subsequently the fugacity of each component in the reacting mixture is simply equal to its partial pressure, and this is where the specific reactor pressure needs to be considered. The standard state fugacity of the pure components in ideal gas form is 1 atmosphere. If we now apply this for our reacting system, for ethanol, its stoichiometric number is equal to 1, that's why it's above the line. It's the partial pressure of ethanol divided by its standard state pressure raised to its stoichiometric number. We are going to substitute 1 atmosphere for our standard state pressure. For each of the reactants, since their stoichiometric number is -1, they appear below the line. We can now simplify this equation to prove that our equilibrium composition mixture is a function of the equilibrium constant at that temperature multiplied by the pressure divided by the standard state pressure. We know the value of our equilibrium constant at 145 degrees Celsius. We also know that all the standard state values for Gibbs free energy and enthalpy that we read of was at 1 atmosphere. And now in this equation, we have 1, 2, 3, 4 remaining variables. If we now write our mole fractions at equilibrium in terms of the reaction coordinate, we can reduce the number of variables in this equation to 2, the pressure and the reaction coordinate. In our stoichiometric table, we now know the amounts initially fed to our reactor, and we can calculate the total amount initially present. We know the stoichiometric numbers for each of the components. So we can now calculate in terms of our reaction coordinate the number of moles that will be present as a function of the reaction coordinate. And now, since we know the total number of moles at any point in our reacting mixture, we can express our mole fractions in terms of the number of moles of each component divided by the total, all of them in terms of the reaction coordinate. After substitution of each of the mole fractions in terms of its epsilon related value and some simplification, we end up proving that our reaction coordinate can be related to the pressure in the mixture and the equilibrium constant at that temperature. We are now going to substitute our system pressure in the same units as our standard state pressure. To give us this quadratic equation in epsilon, and we are going to substitute 1 atmosphere and 2 atmosphere respectively and solve for epsilon. Beware, since this is a quadratic equation, more than one solution is possible. We can now look at our stoichiometric table to determine the feasible range of values for epsilon. In order to make sure that the number of moles of each of the components does not get depleted or go to a negative, which is not possible, we can see that for ethylene, epsilon must be less than 2, for water no more than 1 for epsilon, and for ethanol, epsilon must be larger than 0. Our conclusion is that epsilon must be larger than 0 but smaller than 1. With an appropriate first guess for epsilon in a solver function like in your calculator and values of 1 atmosphere and 2 atmosphere for pressure, we can now obtain the solution. If you're old-fashioned like me, you can use this well-known expression that's used for solving quadratic equations, and this will give me the two solutions. At 1 atmosphere, we can calculate the value for epsilon. It's a very low reaction coordinate, and substitute it into our expression for the mole fractions in terms of epsilon from our stoichiometric table. We can obtain a very low mole fraction for ethanol. At 2 atmospheres, by applying the same approach, we see an increase in the conversion or the reaction extent with an increase in the mole fraction of our product. Once again, we can apply our reasonable person test. According to Le Chatelier, 2 moles in the gas phase reacting 1 mole product, an increase in pressure will force the reaction in the forward direction. Subsequently, an increase in the reaction coordinate with an increase in pressure.